Now we're going to continue with the velocity problem. First, let's go over some physics. Suppose we have a ball, okay, and if you drop the ball, then how do you calculate the average velocity from the time t equal to 1 second to 3 seconds? To do that, we'll take the change in position. So we see from here to here, what will be the change? And then we use that to divide by the time elapsed. So for example, from 3 seconds to 1 second, the time elapsed will be 3 minus 1, so that will be 2 seconds. Okay? So that's how we calculate average velocity. Now, Galileo's law says that if you drop a ball starting from initial velocity equal to 0, okay, then what happened here at time t, the distance that the ball traveled after t seconds from here to here, that's called the position, okay? And this position over here is going to change as the time t change. So it's a function of the time. And we call this a position function for the ball. Now, Galileo's law says that this distance fallen is equal to 1/2 gt squared. And with the g over here being the gravitational acceleration, which is 9.8 meter per second squared. Okay, so half of 9.8 is 4.9. So that's equal to 4.9 t squared. So if you drop a ball at rest, like when the initial velocity equals 0, then the distance fallen will be equal to 4.9 t squared. When you use those international unit, meter and second. So that will be 4.9 t squared. Okay, now this next example over here, we're going to talk about the instantaneous velocity, okay? So suppose a ball is dropped from the upper observation deck of the CN Tower in Toronto, 415 meters above the ground. We try to find the velocity of the ball after 5 seconds. So say here's 5 seconds. What will be the instantaneous velocity at that moment? Okay. Now, how do we do this? Well, first, the instantaneous velocity of the ball after 5 seconds, we're going to denote that by v5. So y at 5 seconds, the velocity y at 5 seconds. First, we know that because the ball is dropped at rest, so the initial velocity is 0. So the position of the ball is given to be 4.9 t squared, which we already went over here. So according to Galileo's law, okay. So that's 4.9 t squared. Now, how can we find the instantaneous velocity at this moment? Well, we can calculate an average velocity near this moment. So, for example, we can choose the time period from 5 seconds to 5.1 seconds, and we can try to calculate the average velocity during this time interval. And then we use that average velocity as an approximation to the instantaneous velocity y at this 5 seconds. So, and then later on, we can move this time, this ending time here, a little bit closer to 5, say 5.01. And then we're going to calculate the average velocity again. And then we even take the time even closer, say 5.001 seconds. So the time interval is going to be shorter and shorter. And then the instantaneous velocity will be approximated by the average velocity, right? We get a better and better approximation when we shorten the time interval. So that's the idea, okay? So let's do this. Let's try to calculate this average velocity from 5 seconds to 5.1 seconds. So that's equal to change in position divided by the time elapsed. Well, what will be the change in position? From 5 seconds to 5.1 seconds, the change in position is from here to here, okay? So we'll take the ending position, subtract this beginning position right here, okay? That will give us this change in position right here. Now, the ending position, the ending time here is 5.1 seconds. So we're going to substitute 5.1 as the time into the t, and we get the ending position. Similarly, we substitute 5 over here into this t, and we get this beginning position right here. Okay, so and then we plug in 5.1 into t, 5 into t, we will get the corresponding position here, and then we subtract. Okay, so as of 5.1, when you plug in 5.1 into t, so that is 4.9 times 5.1 square, and this is 4.9 times 5 square. Okay, and then you subtract them. Do the calculation here, you end up with this number. Notice the unit here is meter per second. So we calculate the average velocity when the time interval is from 5 to 5.1 second. Similarly, we can calculate this average velocity from 5 seconds to 5.01 second, and also from 5 seconds to 5.001 second. Now, as you can see that as this ending time here is getting closer and closer to 5, when you shorten this time interval over here, that's the pattern for this average velocity. And it looks like it's approaching to 49. And then we say that the instantaneous velocity right at this 5 second is going to be 49 meter per second. So that's the end of this problem right here. Notice that there is a close connection between the tangent problem and the problem of finding velocity. If you graph the position function of the ball, okay, graph this one, notice the time can only be 0 and beyond. So I only graph this half a parabola over here. Okay, the time here we don't consider negative time. So this is a graph for this position function. When we calculate the slope, okay, so we try to find, suppose we try to find the instantaneous velocity right at 5 seconds right here. We can, so we can look at the, we can look at this average velocity at a time interval that is close to this 5, okay, from 5 to 5.1. Notice that, as you recall, when we calculate this average velocity at this time interval, that was this expression. But notice this expression is exactly the same expression to calculate the slope for the secant PQ over here. So the average velocity actually corresponding to the slope for the secant. Okay? And as you move this Q along the curve and getting closer and closer to this P, okay, you move this Q closer to P along the curve, and then we will shorten this time period. It's the same as you shorten this time period. So the time period will be 5 to 5.001. Okay, and now as you do that, this secant line is getting closer and closer to the tangent line, and the slope for the secant line is getting closer and closer to the slope for the tangent. And the average velocity is getting closer and closer to the instantaneous velocity v5. Now this is the end of 2.1.